Over the course of this video, these 5 metronomes synchronize themselves seemingly at random. This initially appears to go against everything we've learned in school about entropy and chaos in the universe, and as a result, this video rose to popularity in certain online communities. If we take a closer look though, we'll quickly find that a precise physical mechanism lies behind what appears to be random and unorthodox. I'm Xander.
And I'm Macy.
And welcome. Pay special attention to the platform upon which these metronomes sit. Notice that the soda cans allow the platform to oscillate due to the motion of the metronomes. This oscillation drives synchronization. Without it, these metronomes would simply oscillate completely independent of one another. We'll cover how the platform's oscillation results in synchronization momentarily. Another important acknowledgement before we begin to break the physics of this phenomenon down lies within the base of each metronome. In the context of this problem, we can actually treat each metronome as a simple harmonic oscillator. Each metronome is driven by a pendulum, and each pendulum is connected to a spring mechanism that allows it to oscillate indefinitely. In the context of physical theory, this means that we can treat each metronome as a pendulum that ignores the effects of damping. This is an important distinction to make as it dictates what equations we might begin to use in understanding the system.
If we imagine a system consisting of a single metronome and platform, we can see plainly how these components work together. We noted previously that the movement of the bass allows the metronomes to synchronize. This is a result of the bass motion in response to the movement of each metronome. Because the metronomes are fixed on top of the platform due to frictional forces and the platform freely oscillating, the bass will undergo undamped motion such that the center of mass of the metronome bass system remains in place. This system setup allows us to understand the movement of the bass. When additional metronomes are added, the bass moves with respect to all present metronomes. This results in a direct impact on the movement of the metronome bases, as the movement of the oscillating platform will invoke a force upon each metronome bob. A combination of constructive and destructive interference occurs in the platform's movement, allowing the motion of a single metronome to affect the movement of all other metronomes in the system. This pattern repeats itself until the system reaches an equilibrium point. Over time, this causes their movement to couple and synchronize. Additionally, we will be referring to the harmonic oscillation as nonlinear and self-sustaining. This means that the oscillations of the metronomes are allowed to freely synchronize due to an unfixed phase. To determine the relationship between two metronomes, we must define the phase of each individual oscillator. In any given system, all present metronomes are allowed to begin moving in random frequencies with no correlation, and as explained in the Kuramoto model, the phase will transition from a non-equilibrium state to a synchronized state over time. Back to our two-metronome system, due to the movement of the bass, the metronomes will gradually synchronize with each other in either antiphase or in-phase endpoints.
These endpoints exist because they each minimize the instantaneous effect of the metronomes on each other. An in-phase endpoint occurs when metronomes undergo matching oscillation, and exists because there are no longer any forces acting upon the platform that cancel each other out, changing the course of any metronome's movement. The platform oscillates perfectly according to the movement of all metronomes on it, and there is no longer any spontaneous change in its oscillation. Everything now moves in predictable, harmonic motion, and involves no conflicting forces among the moving parts of the system. An antiphase endpoint occurs when the metronomes oscillate perfectly out of sync with each other. This causes the frictional forces on the platform to cancel each other out, resulting in no movement of the platform. When this occurs, there is no longer any movement or force to counteract the motion of the metronomes, meaning that no spontaneous change in oscillation can happen. The two metronomes will oscillate in phases opposite one another. In cases with more than two metronomes, any combination of in-phase and out-of-phase oscillation may occur at equilibrium.
This is an algebraic form of the Kuramoto model, which is a model developed by the scientific community to predict characteristics in a system that synchronizes itself over time. We will apply this equation later on to model how synchronization progresses. Note that in the mathematical portion of our research, the models describing the motion of the metronome systems are composed of differential equations and derivations that are beyond the scope of Physics 131 course content. The model we have included, though, allows us to model the movement of any number of metronomes in a platform metronome system as individual sinusoidal graphs. This can clearly depict how their movement is affected by the movement of the rest of the system. We will model this under simulated conditions using randomly defined sine graphs to stand for the movement of each individual metronome. We will also apply the Kuramoto model to depict how synchronization would typically progress.
To simulate the use of this model, we time-lapsed ourselves creating an Excel spreadsheet of 3 sine graphs to represent the linear oscillation of 3 metronomes out of sync. We then apply the Kuramoto equation to model how the moving platform affects the oscillation of each metronome individually. The use of Excel allows us to work using the algebraic equation, which is instantaneous, while performing enough calculations to model what the differential equation would otherwise have provided. The end result is a graph depicting the oscillation of these 3 metronomes over a certain time period. Credits go to Stand Up Maths for the walkthrough of using the algebraic Kuramoto equation in Excel, for those of us without much experience working in it.
The Kuramoto model is applicable to other naturally occurring examples of synchronization, such as fireflies all blinking at the same time and aligned menstrual cycles of women in close proximity. Its application can be rather complex when dealing with many individual components of a system, but is what allows us to understand a system even as complex as 100 metronomes oscillating simultaneously. The 5 metronome system seems quite simple at first, but the Kuramoto model reveals how it works.